Hi everyone, Mr. Boltri here bringing you video 3.3, where we're going to talk about quantifying energy. So to do this, first we're going to revisit the conservation of energy principle. Then we're going to introduce something called energy bar graphs and do an example problem using the conservation of energy. So in the previous videos in class, we have derived these energy equations. Kinetic energy is 1/2 mass times the speed squared. Gravitational potential energy changes based on when you change the height, proportional to the force of gravity on the object. And then the spring potential energy is 1/2 times the spring constant times the stretch squared. So now that we have these equations, we can use them to solve problems by applying the conservation of energy. What you'll remember from video 3.1 is the idea that energy can't be created or destroyed, but it can move around. So because of that, we have a closed system, which means that energy doesn't enter or leave. The energy at the beginning is going to equal the energy at the end. And then if energy can enter or leave in an open system, then we're going to have to account for any energy that is added to or taken away from the system. So what this looks like in a more equation form is the energy initial plus work, which is just the fancy name that we give for any energy that enters or leaves the system, equals the energy final. Or since final minus initial equals change, we can just say the change in energy equals the work. So it's going to be really nice if the work is 0, which means that no energy is entering or leaving the system, because then we can just say that the initial energy equals the final energy and solve from there. So to write out all the different energies that we might be dealing with, there might be kinetic energy, gravitational potential energy, elastic potential energy, both at the beginning and the end. And now is as good a time as ever to tell you the thing that I keep forgetting to tell you, which is we actually have a word for kinetic plus potential energy, which is mechanical energy. That's just a vocabulary word that you need to know. I've seen it also referred to in some questions as total energy, but kinetic plus potential energy, we call that mechanical energy. So let's do a problem and introduce something called a quantitative energy bar graph, also called an LOL graph, which you'll see why in just 1 minute. So to do that, let's look at an example problem of a kid who's sitting on top of a frictionless slide 2 meters above the ground. They slide down and we want to figure out their speed at the bottom. So to do this, we are going to draw our 2 energy bar graphs. First for the initial and second for the final. So I just want to say right at the top, you don't have to do this for every question. You can find different shortcuts, different ways that you can do the same thing. I just wanted to give you one example that allows you to visualize the process that we're going to do in a more simplified version. I actually would not recommend you do this process for every energy question you encounter because it's going to take too long and take up too much time, and we need to make sure that we're moving fast on the AP exam. I just kind of wanted to show you so that you could understand. So we list out all the energies that we could have at the beginning, all the energies that we could have at the end. And this circle right here represents our system. And that's going to help us keep track of if any energy enters or leaves our system. So first, we have to be very clear about what is part of our system. So we should definitely include the child and the slide, even though it's frictionless. If it was not frictionless, then we would have to account for the friction of the slide. And then also, and this one might be a little bit confusing, you have to include the Earth in your system because the Earth is what is providing the gravitational potential energy for the child. If we were not to include the Earth in our system, then the Earth would be doing work on the child, which we'll talk about more. But if the Earth is outside our system, then our mechanical energy at the beginning would not equal our mechanical energy at the end, which would be kind of a big headache for us. So if we include the Earth, and we should definitely include our gravitational potential energy reference point, which is for this is going to be the ground. That gives us the delta H above the ground. Then the initial energy is going to equal the final energy, which is good. So now we think about, well, what energy do we have at the beginning? Since the child is sitting, there's no kinetic energy. There's no springs involved anywhere in the problem. So the elastic potential energy at the beginning and the end are both going to be 0. So at the beginning, we just have a bunch of gravitational potential energy. So now we have to make sure that no work is being done in our system, which means no energy is entering or leaving. So we have to sort of check that to see if it might be a positive number, a negative number, or hopefully it's 0. And in this situation, especially since we've included Earth in our system, so gravity is not doing work on our system, then the work is going to be 0. So that means all of the energy at the beginning is going to have to be there at the end. But because the ground is our reference point, there's going to be no gravitational potential energy at the end. And since also no spring, so no spring potential energy, we can say that all of that gravitational potential energy has turned into kinetic energy. So using that information, we can solve the problem. But what's going to look more like when you do this on the AP exam is is really important. I really want you to write the initial and final at the very top. It's like the same thing that we did when we solved projectile problems, where we broke it into the X components and the Y components. I really want you to be very clear about saying the initial and the final energies for each. So the initial energy, and then we can go ahead and fill in all of our zeros. So since it's stationary, 0, 0, no work, and then 0, 0. So that's pretty easy when we calculate the gravitational potential energy by doing mass times the acceleration due to gravity times the height above the reference point. We get 500 joules. It's going to be pretty easy for us to recognize that the final energy is also going to be 500 joules. Since conservation of energy, no energy was created or destroyed, nothing left or entered the system, so the initial energy has to equal the final energy. And once we have the final kinetic energy is 500 joules, using the kinetic energy equation of 1/2 mv squared, it's going to be pretty easy for us to solve for the final speed as the child is at the end of the slide. So this is obviously not exactly 100% correct because frictionless slides don't exist. So there's probably going to be some work done by the friction on the slide, which means some of the energy is going to leave our system as dissipated energy. But this number is a really good place for us to start thinking about how to do conservation of energy practice problems. And we're not going to do work just yet. That's going to be in a couple of videos. So I want you to use the approach. You don't have to use the energy bar graphs. I just kind of wanted you to see that. But I do want you to use the approach of writing out the initial and final and tracing it from there. So I'm looking forward to doing some conservation of energy practice problems with you in our next class. But for now, I'm going to wrap up video 3.3, where we talked about quantifying energy, and go Bears.